This nested diagram situates deep learning within the broader field. A standard machine learning algorithm takes inputs, maps them to outputs, and learns the relationship between those features and labels. For decades, conventional machine learning relied on human engineers to manually handcraft and select the specific features the model would evaluate before processing began. This diagram shows how a simple linear model effectively separates a basic data distribution using a straight boundary line. As the data distribution becomes more complicated, a straight line fails to provide an accurate classification. The model requires a nonlinear boundary to separate the classes. This feature engineering bottleneck makes traditional machine learning methods inadequate for processing raw natural data, like unstructured pixels or audio waves, which contain too many complex variations for manual selection. Deep learning replaces human feature engineering with automated representation learning via artificial neural networks. Through this process, the deep learning algorithm autonomously organizes raw, unstructured data into distinct abstract classifications without needing any human intervention. The result is a highly complex nonlinear boundary, capable of successfully navigating and separating scattered data points in a complex distribution. We can see this capability at scale in the ImageNet dataset. To organize millions of images, the system uses deep layers of representation to amplify relevant aspects while suppressing irrelevant variations. Deep learning's utility comes from this mathematical ability to autonomously invent the specific representations required to solve complex classification tasks. This computational graph maps the perceptron, the fundamental mathematical unit that serves as the building block for larger networks. The forward pass of a perceptron begins with an operation known as the affine transformation. To calculate this, the model computes the dot product of an input and a weight vector. Each input is multiplied by its weight, then aggregated into a single sum. Adding a learned bias term completes the affine transformation, z equals w transpose x plus b. Weights and biases represent the numerical parameters the model continuously updates to bend its decision boundaries around the training data. Moving from abstract diagrams to engineering requires a direct mapping to software implementation. In this NumPy implementation, the class initializes the weight and bias parameters based on the size of the input features. The forward pass executes the affine transformation using a single dot product of the input array and the weight vector, plus the bias. Mapping linear algebra operations directly to array code is what allows for scalable neural network development. After the sum and bias are calculated, the data flows into the second essential step of the forward pass, the activation function. Without this nonlinear step, any deep network would mathematically collapse into a single linear function, regardless of how many layers are added. The activation function transforms the affine sum to produce the node's final output, introducing the necessary nonlinearity to the system. The sigmoid function squashes input values strictly between 0 and 1, but it is computationally expensive to calculate at scale. Modern networks typically use the rectified linear unit, or ReLU. It clips all negative values to 0 while passing positive values through linearly. Over time, certain outputs can become 0 and fail to revive, leading to the dying ReLU problem. To mitigate this, variants like p-ReLU introduce a small learned leak coefficient to prevent nodes from zeroing out completely. Selecting the correct activation function is a critical architectural choice that ensures the network can successfully model complex data relationships across multiple layers. A single perceptron serves as a binary linear classifier, producing a strictly straight boundary line on a Cartesian plot. This creates a mathematical trap. A single node cannot model non-trivial data patterns that require nonlinear boundaries. Solving high-dimensional problems in the real world requires the capacity to chain thousands of these transformations together. Engineers overcome the linear limitations of the individual node by combining them into dense, multi-layered networks. In a multi-layer perceptron, or MLP, perceptrons are grouped into interconnected hidden layers, so the output vector of one layer becomes input for the next. This sequential passing of data vectors from the input to the output layer is defined as the feed-forward process. Each successive layer in the stack calculates increasingly abstract representations of the initial data. Stacking these affine transformations and nonlinearities creates the capacity for the highly complex nonlinear mapping shown here. The feed-forward mechanism transforms simple dot products into a system capable of parsing and classifying high-dimensional data. The final step of the feed-forward process occurs when the data reaches the output layer. The raw output scores from these nodes are mathematically unbound, making them difficult to interpret as discrete predictions. The softmax function is applied as a final activation layer to normalize these raw scores into a probability distribution. This ensures the final outputs sum to exactly 1, providing a clear statistical basis for the network's classification choice. From raw input pixels to a final prediction, the entire pipeline is a continuous chain of vector math, mapping data through layers of nonlinear representation learning.